35 dB and insertion loss of 0.5 dB. If all the ports are matched, find the output powers in dBm at the through port, coupled port, and isolated ports. So you can see that it is one kind of a BLC thing. It's a hybrid coupler. So from port 1, the through port is 2 and the coupled port is 3, and both the 2 and 3 ports will be in 90-degree phase difference of phase quadrature, and the port 4 will be totally isolated. So now take the points from the question that input power is given as 20 dBm, and we know that a coupling should be 20 dB. That means whatever power will be coupled to this port number 3 will be 20 dB down to the input power. And the directivity is 35 dB. And for us, we know the directivity means the isolation minus coupling. So now the insertion loss is 0.5 dB, that is L equals to 0.5, and return loss is infinity as all the ports are matched and we are taking as an ideal case. So we take it as infinite. So now the coupling, what is the coupling? From the power equation, the logarithmic formula 10 log P1 by P3. P1 is the input port power and P3 is the coupled port power. D is 10 log P3 by P4, the coupled port power or the isolated port power. These are the equations that we normally use to calculate the couplings, insertion loss, isolation, and all, and the directivity. Now, what is the power at the port number 2? So that can be found out by this equation P1 minus L, because P1 is the input port, as port 2 is the through port, only the insertion loss will be the factor. So P1 minus L, 20 minus 0.5 will be 19.5 dBm. So 19.5 dBm power will come at the port number 2. The coupled port, that is P1 minus C. So the power at P1 and the coupling factor, that is 20 dB coupling, it is already written. So at the coupled port, the power will be 20 minus 20, that is 0 dBm. And what is the isolated port power? So that is P3. P3 means coupling minus, the power at the coupled port minus the directivity. So coupled port power is 0 and directivity is set as 35 dB. So the isolation will be minus 35 dBm. So this is the answer of the first question. Okay. So it was a very straightforward question. So I don't think you have any problem in this question. So I am moving forward to the second one. This one. This is also a very straightforward question. The design a Wilkinson power divider with a power division ratio of P3 by P2 as 1/3 and source impedance of 50 ohm. It is an unequal power divider Wilkinson design. So these equations are directly written in the book. When your Wilkinson power divider section, you will find one part which is called the unequal power division, and that equation is written here. So the power ratio is 1/3. So K is the ratio factor. So K square equals to P3 by P2. Now from that I can find what is the value of K. Now using these equations, we can find out what are the characteristic impedance of the two branches of this power divider. What is the resistor connected for better isolation, and what are the termination impedances of these two division branch 2 and 3. So using these equations, we can find out the values. So here as well, that ZO3 can be found out by this ZO2 R, and using this ZK K ratio, we can find out R2 and R3. What should be the termination impedances of those ports, power division ports? So this is also a very straightforward question. So nothing to discuss about this because all other equations given in the book. So you can directly use those equations. Moving forward to question number 3. Okay. So what does this question say? So design a lossless T-junction divider with a 30 ohm source impedance to give a 3:1 power split. Again, unequal power division question. So now design quarter wave matching transformers to convert the impedances of the output lines to 30 ohm. Determine the magnitude of the scattering parameters for this circuit using a 30 ohm characteristic impedance. Now see the approach of the solution. We know that the characteristic impedance as 30 ohm as it is given. So power at port 1, if I say it is P1, then the division, the ratio of the power at port 2 and port 3 will be 3:1. So that means in terms of P1, so P2 by P1 should be 3/4 and P3 by P1 will be 1/4. Now we always use the sinusoidal consideration. So that's why if a sinusoidal current is flowing, then what is the input power? P1 should be half into V naught square by Z naught, as Z naught is the characteristic impedance. P2 equals characteristic impedance of the first line. P2 is again the same equation, but instead of Z naught, it will be Z2 because for the second line, the characteristic impedance changes to Z2. But the ratio of P2 by P1 is 3/4. So from this equation, we can also write that P2 equals to 3/4 of P1. Now putting the value of P1 from this previous equation, we will find what is the value of Z2 and it will come out as 4Z0 by 3. That is 40 ohm. That means the characteristic line of port 2 is 40 ohm. The same equation can be written for the port 3 also. The port 3 is half of V naught square by Z3 and also equals to P1 by 4. Now again putting the value of P1, we will find out what is the value of Z3 and it will come out as Z3 equals to 4 Z0, which is 120 ohm. So in normal case for any equal power division, we can see that the 50 ohm line is connected to port 1, and for equal division, the both characteristic impedance of port 2 and port 3 will be like 70.7 ohm. And if you consider the physical length and width of these lines, it will be same. But in this case, these two impedances are different. So if you fabricate the circuit of an unequal power division, you will find that this Z2 line of 40 ohm will be thicker and this Z3 line of 120 ohm will be very much thinner. Now that is Z2 is, if I see from this reference plane where both the ports are connected, we will see the equivalent impedance as the parallel of Z2 and Z3, which will come out as 30 ohm. So that the desired division of the power will be uh, splitted into these two ports. Now, this is the first part. Now, the second part comes like design quarter wave matching transformers to convert these impedances of the output lines to 30 ohm. Now, for the quarter wave impedance section, if I use ZQ2 as the impedance of the second port, characteristic impedance, and ZQ3 as the third port, So from the equation of quarter wave, we can find out ZQ2 equals to under root Z0 Z2. The Z2 is found out from these equations, and you can put it there. It will come out as 34.6 ohm. And for the third one, ZQ3 under root Z0 into Z3. These very straightforward equations for a 90-degree line, that is a quarter wave transformer line, and it will come out as 60 ohm. So for quarter wave matching, you can use these two impedance lines with 90-degree length to match those ports to 30 ohm characteristic impedance. Now, the last part of the question comes like determine the magnitude of the scattering parameters for this circuit using 30 ohm characteristic impedance. For the scattering parameters, we will use these equations. So S11 for this structure, we know that 30 ohm is connected at this port and the line is also a 30 ohm impedance. So from ZL minus Z0 by ZL plus Z0, that will come out as 0 because this port is matched. So S11 is 0. Now coming to S22. If I see from this port, from port 2 towards the junction of these two ports, so we will see that the port 1 line and port 3 line will be in parallel. So for 30 ohm line and 120 ohm line is parallel. So for that case, ZL will be 30 parallel 120, Z0 is Z2, that is 40 ohm. Then from ZL minus Z0 by ZL plus Z0, we will find that S22 is minus 0.25. And the same case from the third port, if I look from this port 3 towards the junction, we will see that port 1 and port 2 are in parallel. So ZL will be 30 parallel 40, and putting that value into this equation, ZL minus Z0 by ZL plus Z0, we will find S33 is minus 0.75. Since all the ports are not matched, the network is lossless and it can be reciprocal. So if it is a reciprocal network, then we can say S12, S21 is same. And from the unity equation, we can find out that the magnitude square of the magnitude of a row, the summation of the magnitude of a row is 1 from the unity equation of lossless reciprocal network. So from S21 or S12, we can find out the ratio P2 under P2 by P1, as these are the voltage reflection coefficient. So we have to take the under root of P2 by P1. That will come out as 3/4 root under 3 by 4, which is 0.866. And the same we can find out for S31, which is 0.5. Now put these values in this unity equation and you will find out what is the value of S23, that is the isolation between this 2 and 3, and it will, the magnitude will come like 0.433. And as it is reciprocal, the S21 S12 is known same, S31 S13 is also same. So all the 9 elements of this matrix can be found out. So this is the third question. Now moving forward to the fourth one.
Sir, I have a
Here,
doubt in the third one.
yeah, yeah. Tell me.
Sir, like if we look into the second port, port 2 in the previous
Yeah,
question. Sir, so we see that there is a load at the end, right, which is 30 ohm parallel 120 ohm.
which this one you are asking, no?
Yes, sir. If
Ah,
we look into port 2 without adding the transformer, we see
yeah,
that at the end of the port there is a load, right? 30 ohm
yeah.
parallel 120 ohm.
120. Yeah.
Sir, so when we add the quarter wave transformer, then like why do we use the formula that root over 40 into 30, like shouldn't the
This,
quarter wave transfer?
yeah, actually, there are two parts of this question. One part is that you are going to match these Z2 and Z3 to the 30 ohm. Okay, so for that we need a quarter wave transformation. So as it is shown in the design, a quarter wave matching transformer to convert the impedances. So if we use a matching, then we have to include this quarter wave transformer. But in the third part, they haven't considered that. They have said that the both the ports are unmatched. It is also written here. So that's why only the values that we calculate from the first, that is Z2 and Z3, we consider these values for the calculation of the scattering parameters. That's why we don't use, because for that, if we matched already, the S22 and S33 will be again zero like S11, right?
Yes, sir. So
But
it's not matched, right? Like we are not
it,
matching the circuit. We are only converting it to 30.
yeah, because there are two parts. For the first part, it is saying if you want to match, then what should be the length, characteristic impedance of the quarter wave matching. And in the second part, they are not considering the quarter wave matching. They say it is unmatched. Now you calculate the S parameters. So that's why you can find out that S22 and S33 are also unmatched, and it is showing some reflection. If it is, if it was matched, then there should be zero as S11 because S11 is already matched. Okay,
Yes, sir. Thank you.
so moving to the question number 4. So this is the question of a attenuator. So you can see that there are two types of attenuators shown. One is a T network, another one is the pi network. Now they are considering the characteristic impedance as 50 ohm and different attenuation levels of 3, 10, 20 dB. So now the question is, these attenuator levels 3 dB, 10 dB, 20 dB, what will be the design equations or what will be the values of the R1 and R2s from these two circuits? Now this is a very rigorous question. You have to calculate many formulas here. So one thing you can do, so for attenuation, you have to find out the scattering parameters. As attenuation means the port 2 will be attenuated. That means S21 will be 3 dB, S21 will be 10 dB, or S21 will be 20 dB. So for that, you need to calculate the S parameters of these circuits. And how can you calculate the S parameters? Either you can calculate manually by putting one voltage source, current source here, and then you can calculate the S parameters. But the easy way is to calculate the ABCD parameters of these circuits and then convert the ABCD parameter to S parameter as it is shown here. So to calculate the ABCD parameter of the total circuit, you have to divide the circuit into three parts. Suppose for the first case, for the T network, only this R1 consists of one network, this R2 consists of another network, and this R1 consists of another network. The three parts. You take the three ABCD parameters of these three parts, cascade it, and multiply, because this is the ease of calculating the ABCD parameter of a whole network. So calculate the singular ABCD parameters of a separate networks and then cascade it, multiply it, and you will get the overall one. So this is how the ABCD parameters are calculated from this network. The steps are not shown here. You can find out, it is already given in the book, in the David Pojar's book, that for a series impedance Z, what is the ABCD parameters? 1, Z, 0, 1. For parallel 1, 0, Y1, like that. You just write side by side and multiply it, you will find the equation. You will find the final matrix. From there you can find A, B, C and D values. Now what are the equations for S11 and S21? So the S11 equation, transformation equation is A plus B by Z naught minus CZ naught minus D by A plus B by Z naught plus CZ naught plus D. Put those values here and use this equation S11 equals to 0, as it is shown that input and output are matched. So that means S11 is 0, S22 also 0. So S11 0, you will find one equation for R2 of consist of Z0 and R1, because only two variables are unknown. So we need two equations. One equation will come out from this S11 and the second equation will come out from the S21. Now let's see the S21 equation or S12. So the S12 is that 2 by A plus B by Z naught plus C by Z naught plus D equals to alpha, because alpha is given here, that the ratio of output voltage to input voltage, that is the attenuation factor actually, alpha. So from here also put the A value, B value, C and D. You will find this equation. Now manipulate the equation using the value you got from the previous one, R2. After manipulating, you will find one equation which is solely consists of R1. So by variable separation, you can find out what is the value of R1. R1 equals to Z naught by Z naught into 1 minus alpha by 1 plus alpha, and put this R1 value into this equation, as you will find that Z R2 equals to Z naught into 2 alpha by 1 minus alpha square. This intermediate steps are avoided, so you have to calculate it by your own, because you will find that after this equation, from see that r1 square plus z naught square, you can put these values there, interchanging the values, and you will find a simplified form of this r2 plus r1, like that. Now again you have to use the value of r2 to find out this equation. So you got the design equations of R1 and R2 for the T network. Now you know that for three different levels, different attenuation levels, you have to find out the values of R1 and R2. So for 3 dB, it is a logarithmic scale. Now convert it into the linear scale, it will come out as 0.708. Now put this value in these two equations, you will find R1 and R2. We continue the same process for the other two values also. Now for the pi network, the same process you have to follow. First of all, calculate the ABCD parameter of the whole network, then convert it into S11 by using the same equations. Again the condition same, S110, because all the ports are matched. You will find one design equation for R2 or R1, whatever you can say. Now again S1 to use that, uh, it will be, it will give you another equation, and put the values from the previous one, that is R2 equals to 2 z naught square R1 by R1 square minus z naught square. You will find out one simplified equation, and then again manipulating, you will again find out the two equations for R1 and R2, which will come out like z naught into 1 plus alpha by 1 minus alpha, and R2 will be z naught into 1 minus alpha square by 2 alpha. And it is already told that z naught you have to use a 50 ohm, and again you put the values of r alpha, you will find out the values of r1 and r2 for the pi network. So this is a very rigorous question. You have to calculate these equations, because in between this equation and this equation there will be two equations, so that is avoided here. So you just do that by your hand and you will find out how this equation comes from here to here. just to put the values from the previous one. Okay. Now moving forward to question number 5, it is the matching network problem. Again, using the Smith chart. So a load impedance of 90 plus J60. Okay, the question, this picture is not from this equation. You avoid this picture. Okay, so a load impedance ZL equals to 90 plus J60 is to be matched to a 75 ohm line using a single series stub tuner. Find two designs using open circuited stubs. Now, how to approach this question? First of all, what you have to do, you have to normalize that ZL by this 75 ohm, and it will come out like this. Small ZL equals to 1.2 plus J 0.8 ohm, and you mark this point into the Smith chart, or it will come out at the point A. Okay, so the normalized impedance of the load network is marked here. The second step is to draw a constant VSWR circle by taking this Smith chart center as the center. So if you draw a SWR circle, you will find out that the circle intersects the 1 plus J0 line, that is this line, R equals to 1 and 1 plus Jx, sorry, R equals to 1, and the reactance part will change. So it will intersect this 1 plus Jx line in 2 points. First point is B, and second point I will show it later. So now what you have to do, you take the intersection point here and connect one line from the center to here, extending to this point at the outer side of the Smith chart. From this point you can find out that what is the reactance part of this point. So that will come out as minus J 0.753. It is around here. So now you have to compensate that. First of all, you have to come to 1 plus Jx circle to match the load impedance. You have to first come to 1 plus Jx circle, then you have to go towards the matching point. So to come to 1 plus Jx circle, what is the distance you have to travel? That you can find if you extend this point. So suppose from the center you connect one line to here and then extend it to here. At the outer circle of the Smith chart, you will find out the lambda value. So for this case, the lambda value will be 0.172 lambda, and for this point, this lambda value will be 0.346 lambda. So you have to travel this much length, 0.174, and this length means you have to put the stub at this distance from the load. So the stub position from the load you have to find out from this, so that the locus of this load impedance will fall on the constant R circle, that is 1 plus Jx. Now you have to compensate the reactive part. The real part is done. Real part is matched to 1. From 1.2 it comes to 1, but the reactance part is not compensated. It has a new value of 0.753. So what you have to do, you have to compensate this 0.753 by the complex conjugate of this. So the complex conjugate is plus J 0.753. And what will be the length of that open stub to find out this plus j 0.753, that you can calculate from this open circuit point to this point. Here you can find out the lambda value is 0.25 because the total circle is zero point 0.5 lambda and half cycle is 0.25. From 0.25 you calculate it here, then there. So it will, sorry, it will come out like the series open stub Z1 requires reactance of J 0.753 ohm. That is a complex conjugate of this, and it will follow along the outer edge towards generator. You have to go to clockwise direction to reach at this point, and the open stub length will be 0.25 plus 0.103 lambda. You can find directly from here. So that is 0.353. This half cycle is 0.25. This take this because this half cycle will come out as 0.25, and from here how much you are going? You are going 0.103. So the total length will be the stub length, and the impedance is shown here. So from that you can find out what should be the stub length and what distance the stub will be connected to the load, and the impedance of that stub. So this is the first point. At the first, if you take the other intersection point of this VSWR circle to 1 plus JX circle, then what will be the design equations? So this is like that. Now here the second point is considered. The first point was here, one first intersection point was here 1 plus jx. The second intersection point comes at this point, b equals to j 0.753 positive. So again the same process you have to follow, that at what distance the stub will be connected. Okay, from A to B, you have to go from this point to this point in clockwise manner. So you connect the lines from the center and extend it to the further to edge of this circle for the both the cases. Take the values of the outer edge and you will find out what is the length. Here the equation is 0.5 minus 0.172 plus 0.153, or you can take the values from here also, because this thing will give you 0.25. Okay, 0.25 is there. From here, if you extend it to there, so from this point to this point you calculate the value by 0.25 minus this point, and from this point if you connect here, so from this point to this point you will get the actual value because this is 0. So just calculate the distance, so you will find out that at which distance this stub will be connected. Now what should be the length of the stub? So again the same, because for this point the reactance part is j 0.753, but we want to compensate that by adding one complex conjugate reactance of this. So the complex conjugate is minus j 0.753. Then what should be the length of the open stub to find out this complex conjugate impedance of this reactance? So that you can calculate from the open circuit point to minus j 0.753 point, and at this point the lambda value is 0.397, and at this point it is 0.25. Just subtract that and you will find out that the length of the open stub will be 0.147 lambda. So for a single impedance, you have two different matching networks, and you can choose any of the matching networks to match the impedance. So for first one, what happened? Yeah, for the first one, you can put the stub at 0.174 lambda, and the length of the stub will be 0.353 lambda. And for the second one, you can add the length, you can add the stub after 0.481 lambda, and the length of the stub will be 0.147 lambda. You can use in either of these equations. Now the second question. Here, the circuit is given here. This is for the question number 6. You can take that. So in the circuit shown
Uh,
below,
in the
hello,
question, yeah,
yeah,
I just want to clarify one thing. That
yeah,
we were doing the previous question that was for a series stub, right?
yeah.
So in a series stub, we only need we only.
Mm, go again. I can't hear. Hello.
Hello. Yeah.
Uh,
I said that in a series stub,
yeah,
we only do calculation on a impedance.
your voice is breaking.
Yeah, I think someone is muting me. But ठीक है. No, I am saying that in a series stub, the
Yeah,
calculation has to be done wholly on a impedance Smith chart, right?
yeah,
And
yeah.
in like the question,
Shunt stub.
yeah,
Yeah,
and in a shunt stub, we have to first
convert that into admittance Smith chart.
and the only difference in that is the position of ZOC and ZSC changes, right?
Yeah, yeah, yeah.
There is no other change, right?
No.
Thank you.
But normally, if you find any Smith chart in market, you will get that impedance and admittance chart in a same Smith chart. Otherwise, if you take this impedance Smith chart, then for shunt stub case, you have to first draw the G equals to one circle accurately. Then from the load locus, you have to find out the intersection point to Z equals to one circle. For this case, I have considered R equals to 1. For the shunt case, you have to consider the G equals to 1, the same circle at the other end. And for that, open circuit and short circuit positions will be changed, and according to that, you have to calculate the length. Now the question number 6. So the question number 6, it is saying in this circuit shown below, I'll show you the circuit again. You can see the circuit, there's a 40 ohm connected, I mean the 40 ohm transmission line. Then there is a line section of L, that is Z1 for the matching purpose, and the load is ZL equals to 200 plus J100 ohm. Now going to the question again. In the circuit shown below, a load ZL equals to 200 plus J100 ohm is to be matched to a 40 ohm line using a length L of lossless transmission line of characteristic impedance Z1. To find L and Z1, determine in general what type of load impedances can be matched using such a circuit. So the 2 points you have to find out: what is the length of the matching section and the characteristic impedance of that section. So you know the telegrapher's equation. So just put that value there. So to match this load, we must find out ZL and L. So Zin we know that 40 ohm as it is given. So it give Zin equals to 40 ohm, and it will be like the equation is Z naught into ZL plus J Z naught tan beta L by Z naught plus J ZL. Now you put those values, and for this case Z naught is Z1, which is unknown for the matching section. ZL is 200 plus J100, and JZ1 tan beta L. Here tan beta L is given as T. And you will find out this equation. It's a mixed equation, so, and there are two variables. So what you have to do, we have to equate the real part and the imaginary part. So equating the real part, we find out 40 Z1 minus 4000 T equals to 200 Z1. So from here, we can find out Z1 as minus 25 T. And from this imaginary part, we can find out the T value. T value will come out as plus minus 4.1. But we want Z1 to be positive. So for to make Z1 greater than 0, we have to take the negative value of this T. So T equals to minus 4.1 is taken, and from this equation we can find out what is the length of that line. So beta L equals to tan inverse minus 4.10, which is coming out as 76.3. Now 180 minus this will come out 103.6 near about, and L will be 0.288 lambda. And the characteristic impedance, you put this value into the first equation minus 25 into T, you will get 102.5 ohm. Now the comment is that determine in general what type of load impedance can be matched. So the comment is that not all the load impedances can be matched in this way, because that this T value will have a defined value. For this case, it is realistic, but for different matching problems or matching load impedance, this may not be a realistic value. So for that, not all the load impedance can be matched with this technique. We have to take Z1 to be greater than 0 and L also be. So that is the part. Now moving towards the seventh question. This question, the upcoming two questions are related to amplifier and the nonlinear properties, that is noise, figure, and other things. So the first of this question is an amplifier. You can see the diagram here. An amplifier with a gain of 12 dB, a bandwidth of 150 megahertz, and a noise figure of 4 dB feeds a receiver with a noise temperature of 900 K. Find the noise figure of the overall system. So first take the values what are given. That is, gain is given as 12 dB. In linear scale it will come out as 15.1. Bandwidth is 150 megahertz, noise figure as 4 dB, and in linear scale is 2.51. And the receiver noise temperature is 900 K given. Now use the equations. If we take the room temperature T naught as 27 degrees centigrade, and in Kelvin scale it is 290 Kelvin, on the equation of noise figure at the input side of this receiver F2 will come out as 1 plus TE by T naught. T is the effective noise temperature of the receiver and T naught is the room temperature. You will find out the noise F2 as 4.1. And for cascading system, what is the overall noise figure equation, that is, if I say it is at f1 and the gain is g, then f1 plus f2 minus 1 by g will be the overall speed of the system. And we know f1 has 4 dB, which is 2. And f2 we find out from this equation 4.1, and g has for 15.1, or it is given here. I think it is wrong here. You can verify it. I think it is 15.1. It should be here. So which will come out as 2.71, and in dB scale 4.3 dB. So the process is very similar, but the values you can verify once. This is the straightforward equation you can use for the overall noise figure, which is given there in the book. And now from this equation you can find out the overall noise figure of the system. So this goes the first question. This is very a simple question. So in the second question, you have to do some mathematics. So let's see what the question says. A balanced amplifier circuit is shown below. The two amplifiers are identical, each with power gain G and noise figure F. The two quadrature hybrids are also identical, with an insertion loss from the input to either output of L greater than 1, not including the 3 dB power division factor. So derive an expression for the overall noise figure of the balanced amplifier. What does the result reduce to when the hybrids are lossless? So that there are two parts. First of all, we have to derive the expression of the overall noise figure, and then we have to put this condition if it is a lossless network. So for finding out the noise figure of the overall system, we have to consider few things. That is, if voltage and noise after the first and second quadrature, that is, this one is the first quadrature. After it, that means at the input side of these amplifiers, and the second quadrature means at the output side of the amplifier. So V1 N1, V2 N2. So you can see from the second picture that V1A N1A is for the first amplifier, and V1B and N1B for the second amplifier, and the same for V2A N2A, V2B N2B. Again, approximation for sinusoidal equation, sinusoidal voltage and current source. So if I take the Vi as the input voltage coming at this input port of the first quadrature, then what is the signal power? The signal power is Vi square by 2. Now, then what will be the power at the through port and at the coupled port? In voltage term, it will come out as Vi by root 2L. L is the insertion loss, or the yes, the L is the insertion loss is given. So at this point, at the first, at the through port, that will be Vi by root 2L, and at the other coupled port, that will be minus V1B, which is minus JVI by root 2L, because these two ports are 90-degree phase quadrature. So that's why this minus J term pops up here. Now at the output of the first amplifier, what will be the voltage V2A? That is Vi by root 2L, that is V1A into root G, because G is given as a power gain and we are dealing with the voltage. So we have to take the under root value of the gain. The same for the V2B, minus J Vi root under G by root 2L. Hence the output voltage is, because all the outputs are coming at this point, So if I consider these two equations, it will come out as V naught is minus J V2A by root 2L, this port coming here, and for V2B there will be no phase lag ideally, V2B by root 2L, and putting these values V2A and V2B, you can find out that minus j v1 vi by root g by 2l minus j vi by root g into 2l, so the same part, which is equal to minus j vi root g by l, and the power magnitude of the power is this square by 2, that is vi square g by 2l square, which is vi square by 2, that means the input power si. So S naught will be GSI by L square. Now for the noise figure N1A, that is at the input of the first amplifier, and N1B is the noise figure at input of the second amplifier, which are same. So N1A equals to N1B equals to K T naught B is a system noise normal. Now N2A and N2B, that is after the amplifiers, will be K T naught B into G, the gain factor, and K TE into BG, which is the effective noise temperature of the amplifier, and which will come out as F minus 1 into T naught. You put the value here, you will find out what are the values of N21 and N2B, which are also same. So for the noise figure at the output side, it will be, output side means at this point after the second quadrature, it will be N2A by 2L plus N2B by 2L plus N added. N added is the extra noise due to the second hybrid. N added can be calculated as 2 KT naught B into L minus 1, because there is a loss which is L. So we can check from the book that if a lossy network with a loss of L, the noise figure will come equal to F equals to L. So here, instead of F minus 1, it is shown as L minus 1. Now substitute this value N added to this equation, you can find out this N naught equals to KT naught B GF by L plus KT naught B into 2L minus 2 by 2L. And the overall noise figure, that is the input SNR by the output SNR, you can find out input SNR is SI by NI and output SNR is by S naught by N naught. In simplification, it will come out as SI by N naught by S naught into NI. SI by S naught, you can find from this equation, that is G by L square, sorry, L square by G, L square by G. Now N naught by Ni. Ni is KT naught B and N by N naught. So it will come out as, if you KT naught B take it common and divide it by KT naught B, that will cancel out. It will come out as GF by L into plus 1 minus 1 by L, which will simplify as LF plus L by G into L minus 1. So this is the overall noise figure equation. Now putting the lossless condition, if the hybrids are lossless, that means the loss is 1. So then the equation will fall F total equals to F. So here the second, the last question of this tutorial ends. So you go through the tutorials first, and if you find any problem, you can ask me, or you can ask a professor in the class also. So this type of questions you will find in your next class test. or